Hello and welcome to today's session. We're looking at nuclear decay and in particular nuclear decay modes. Objectives are to interpret the NZ chart for radioactive isotopes and to know how alpha, beta minus and beta plus decay are represented on the NZ chart or graph. A good way to visualize nuclear stability is to plot the neutron number versus the proton number for all known isotopes. And we call this the NZ plot. So looking at this, the dotted line represents N equaling Z, so the number of neutrons equaling the number of protons. The blue line is the stability line where we've got stable isotopes. And you'll see on there as well, we've got three situations, A, B, and C. So situation A is for isotopes above the stability line. So they're above the stability line and they've got less than 60 protons. The proton number is less than 60. And what they tend to do to get to that line of stability is emit a beta minus particle, so beta minus decay. For isotopes below the stability line, again, Z is less than 60, they tend to emit a beta plus particle, so a positron, and that's to get towards that line of stability. And then for much heavier isotopes where their proton number is greater than 60, you have these very large, unstable isotopes. They tend to emit alpha particles, so situation C, and that's to come down towards more stability, towards the blue line. So we've got these situations that we can look at for these isotopes. So we can look at how an isotope will decay by looking at where it is on the stability line. It gives us a good indication of stable isotopes and what the unstable isotopes are going to do in order to become more stable. So which type of decay are we going to look for? So a few pointers on the NZ plot. Very light elements where Z is less than 20, N is roughly equal to Z, so they're very stable, so light elements. As that Z number increases greater than 20, the neutron to proton ratio increases. More neutrons are required for the strong force to overcome the Coulomb repulsion. So we know protons are positively charged, and if you've got lots of protons in there, there's going to be a lot of repulsion. And as they get heavier and heavier, they're going to become more unstable. So they're going to have more neutrons and protons, but they're going to be very large, which means the strong force between the nucleons is unable to overcome that Coulomb repulsion. So they're going to become unstable and start emitting alpha particles. So you saw that on the graph, and that happens when Z is greater than 60. So when Z is greater than 60, you've got these heavy, very heavy isotopes with loads of neutrons, and there's not enough strong nuclear force to hold them together to overcome that Coulomb repulsion. Yeah, so we can summarize it in 3 points. Alpha emitters, Z is greater than 60, beta minus above the stability line, and beta plus below the stability line. So this graph shows thorium-232 and the decay chain process. So you can see initially 23290, and then because there's a high number of protons, it's going to emit a alpha particle. And then you can follow the chain. You can follow the chain of decay. So seeing whether there's going to be an alpha decay, beta minus, or beta plus. So you follow the decay chain down and you can see that process. All the time, the nuclear isotopes are trying to become more stable and get towards that stability line. So when we have these nuclear decays emitting an alpha or beta particle, the daughter nucleus that's present may be in an excited state, and when it de-excites, it can emit a photon. So a common question will be to calculate the photon wavelength, and the calculation works exactly the same as electrons making transitions between atomic energy levels, but this is just taking place in the nucleus. So we can use the exact same problem solving process that we've looked at in year 12. We have cesium, and when it decays, it has an excited daughter nucleus, barium. When this daughter nucleus de-excites, it releases a photon, and we need to calculate that photon wavelength. So we can use the equations from year 1. So we know photon energy, E is equal to HF, which is the same as HC over lambda. We've got a difference in energy levels, so that's going to correspond to the energy of the photon. So in order to find this wavelength, lambda is going to be equal to the value of HC over E. We've got energy in mega electron volts, so we need that in joules, so dimensionally we can get to the wavelength being in meters. So if we get that in joules, then dimensionally it will work out to have wavelength in meters. So 6.63 times 10 to the minus 34 times the speed of light, and then we need the difference in these energy levels. So 1.172 minus 0.151511, and it's mega electron volts. So we can convert that into joules by timesing it by 1.6 times 10 to the minus 13, because it's mega electron volts. This will give us the wavelength value. So all you need to do is put that into your calculator and you'll find the wavelength. So I'll do the calculation now. And we'll go to three significant figures. Yeah, three significant figures. We'll go to three significant figures, and you get 1.88 times 10 to the minus 12 meters. So just check, remember that one electron volt is equal to 1.6 times 10 to the minus 19 joules, just so you're happy with the conversion. So that means 1 mega electron volt is equal to 1.6 times 10 to the minus 13 joules. And the only other thing was the bit there when I said HF is equal to HC over lambda. So remember that the wave speed of light is equal to frequency times wavelength. So frequency is equal to C over lambda. So just things to note for that. Again, we've got another way to look at how these isotopes are trying to become more stable. So this is another way to visually represent what's happening. We can see if we've got an unstable isotope X, there's various ways that it tries to become more stable. And in this graph, we can show the emission of gamma as well. So remember when the isotope's emitting gamma radiation, gamma is just a high energy photon. So that's going to reduce the energy level of the isotope. So just another way to visually show an isotope trying to become more stable. Okay, to summarize then, we've seen that a graph of neutron number against proton number shows that there are more neutrons in larger nuclei. This is needed to ensure the stability of the nuclei. And gamma rays are given off. So gamma rays are given off by the excited nuclei after they emit an alpha particle or a beta particle. So that can happen anytime this excited nuclei decays, can give off gamma radiation in order to become more stable. And the other thing as well is calculating photon wavelength. So when you're given energy levels, you can find the photon wavelength. Remember, this is energy in terms of the nucleus, so the nucleus trying to become more stable. So your tasks for today are to make notes on the technetium generator and define what is meant by a metastable state, and to complete summary questions 26.8 and submit them via Turnitin. As usual, if you've got any questions, send me a message on Teams or drop me an email. Thank you for listening.